right, the next thing we want to talk about is refraction. We talked about reflection, and here's, again, one of the links, the Canvas links, one of the apps, the Fizzlets. And so what this one lets us do is, again, incoming ray, and we can vary the incoming ray. And you see we get two beams. We get a reflected beam, which these two angles are equal, but we also get one that goes in if the material is clear. Turns out even if it's not clear, but if it's clear, we might be able to see it. And so even in glass, we'll have another ray that is refracted. That's the one we want to talk about. We'll call that angle theta r or theta 2, and you can see that they're not equal. Well, the way to think about that, and the example I always use is, a lot of you have been in the band maybe, and so you form rows and you march. Imagine you're on a parking lot, a hard surface, and you're going to march into the mud. The band director's pissed at you and he's going to make you march in the mud. So you're marching straight, you hit this border at an angle, everybody slows down in the mud. These people that aren't in the mud yet keep going. So the line bends because one end of it is slowed down. And in fact, you use that geometry and the fact that line is the same to work out the relationship between the velocity and the angles. And that's the basis of what we're going to call Snell's Law. So if you hit a region where it's slower, then you're going to bend down toward this normal. If you were to speed up, then these would go further and you'd bend away from the normal. That's refraction. We're going to characterize it in a thing called the index of refraction, which is simply the ratio of the speed of light in vacuum to the speed of light in the medium. Light often travels slower in various mediums than it does in a vacuum. So that number is typically going to be bigger than 1. For vacuum, n is 1. For other media, it's going to be bigger than 1 because the number on bottom is going to be smaller than the speed of light. It's a ratio, so it has no velocity, has no unit. There are some typical numbers. See, diamond, zinc, glass, which has a small, the bigger the index, the more the bending, we'll see in a minute. Water's in here somewhere, 1.33, diamond 2.4, and then various gases. Air does have an index of refraction a little bit different than 1, and it's a strong function of density, temperature, and humidity. That's what it would be at 1 atmosphere pressure, 0 degrees. So if we go from fast to slow, it bends toward the normal. And it says to go back and look at our link here. So we got our index of refraction is higher. Now this is reversible, so if I were to put it here, it would go out. So if I'm going from slow to fast, it would be bent away from the normal. And then again, if you go from slow to fast, so that this one is actually faster than your refracted ray, the theta 2, angle theta 2, again measured relative to the normal to make it easier to talk about curved surfaces, you're going to be bent away from the normal. So now what happens is, remember the frequency is sort of the source. So as a light beam passes from a medium of one speed to another, the frequency stays the same. The velocity changes. That means what? That means that the wavelength changes. So the effective wavelength inside the medium is, if you write them down and divide them, you get this relationship. I think there's a homework problem about that. The ratio of the wavelengths is the ratio of the index of refraction. So if one of the mediums is air, then you could solve for lambda is n times lambda n. I think one of the homework problems will probably have you do that. We go back to the form, what we had earlier, the picture, and replace the velocities with the index of refraction, then we get what's called Snell's Law of refraction. Nobody really knows who discovered it. Ancient civilizations, they didn't have trig, but they were aware of the bending of light. It's usually accredited to somebody ain't Snell, but people knew of it before him, just not in that particular form. It was called Snell's Law. So here's an example of the type problem that we'll do. We'll have an incoming ray, they'll give us the angle of incidence, and we'll predict what the refracted ray is. So basically you just identify your angle, identify your index of refraction. So we're in air here, which is 1. We're coming in at 30 degrees. We know that this is glass, so we look up the index in that table, 1.52, and then you just plug them in, 1 sine 30, 152 sine theta 2. So I can solve for sine theta 2. You first take 1 over 152, take the sine of 30, multiply, get a number, and then you'll take the inverse sine of that number. If your calculator's in degrees, which you'll need to be careful of on the test and on the homeworks, then you'll come out and refracted, and notice that, yeah, it came in at 30 and it bends out at 19.2 degrees. Now, it turns out that index of refraction for many materials is a function of color, and I think we'll pause here and put that on the next video. We'll pick the next video up here. So see you in the next video.